So it's a very good question in the break, namely, does this only work for probability distributions? No, it works actually much more generally than that. Basically, any quantities that you can manipulate with a, with a semi-ring, you can do this with. So, for instance, for shortest path planning, well, these might be kilometers or miles or whatever, or just shortest path in a tree. You would have exactly the same setting. Likewise, for instance, the fast Fourier transform, you can actually reinterpret it as an example of a really efficient algorithm on a semi-ring. So the Paksad, Bayam, and a few others who wrote the original generalized distributive law paper have that actually as an example in it. I would nonetheless strongly recommend that you first read this paper before you read the generalized distributive law paper. This is a lot easier reading, and after reading this, the other one will become easy reading too. The converse order is not true. At least not, it wasn't for me. And unfortunately, this came out later. Okay, so here's what we get, right? So exactly the same that we had on, this, rather than a chain, we now had a tree. By the way, is the recording on? Is the recording on?
Yeah.
Good, thanks. So now we get the same mess, and now wherever we have product, we have sums, and we're taking the max over there. Now that max operation may be much easier to compute than summing over everything. And so we have if I take the max over x5, well, I just have f some function of 2 and 4 left, and here I have something in terms of 2, here I have 4 and 5 left. And this entire expression then gives me, whatever message of 2 and 4 I would be sending to 2, 3, and 4. So it's exactly the same thing that we saw before with, probability distributions. And you would care about that, for instance, for finding a maximum likelihood annotation of, whatever latent variable model that you have. Goes without saying that, you shouldn't have loops. So that would be like the situation that maybe I will choose to do whatever next person does, and that one chooses whatever the next person does, and so on and so on. And if we close that loop at some point, well, it doesn't necessarily give you the maximum solution. So you could actually get situations where this, will be my model, and whichever way you start with, you might get one or the other solution. People just use it often anyway, and well, that's for instance for turbo codes and so on, where this is actually in a lot of use. So if you use a mobile phone, this is probably in use. And there's a lot of very beautiful theory why, even though you're not really supposed to do it, it works anyway, and there are actually nice, good guarantees for that. So that's become a very fertile field of information theory. Now, an obvious thing that you can do is you add an edge, and now things are okay. And that edge essentially captures that dependence that you would have had otherwise, and everything's clean again. But of course, the size of your state blows up. So this was probably fairly abstract at the moment. I hope it'll be more understandable as you go and use it in practice. So now let's actually take a step back and move to something a little bit more practical. Let's say we do clustering. And yep.
One question about the max plus semi-ring, just for the sake of the last step of normalization. So would I, instead of just dividing by the sum, I just divide by the max over all the distribution of numbers I got?
Well, in this case, you don't need to divide necessarily. So for instance, if I want to find the shortest path from Berkeley to San Francisco, and I have, a graph of, how I can get from A to B. For instance, I can go from here to the BART station, and then from the BART station to, let's say, Powell Street, there's a certain distance or cost involved. You actually care about the sum over the entire path. It might cost you some taxi fare or a few minutes to get from here to the BART station, and some other few minutes to get to San Francisco. So in that case, you don't really need to renormalize. Whereas if I wanted to have a probabilistic distribution, if you at each step do a random thing, or maybe not entirely, uniformly at random, but maybe you walk out of the door and you think, okay, should I take a cab or not? Well, cabs are expensive, maybe I'll just walk. You walk down, a road. You decide again, well, okay, maybe it's starting to rain, I take a cab. So you design a random walk. In that case, in the end, your limit distribution that you're going to get, you still actually want to normalize that out to 1, such that you say, well, you're going to end up in San Francisco eventually, that the sum over all the paths actually is 1. Because you cannot have just halved or doubled on the way to San Francisco. It's just still only you. It's just that you have distribution over paths. Now let's actually take a step back and do something much simpler. We'll just do clustering, right? So this is how we're going to practice variational methods. Afterwards, we'll apply them to hidden Markov models. And the extension from hidden Markov models to more general problems is essentially then left as an exercise to the reader. For a while, that was probably about 10, 15 years ago, it was very well possible to write a lot of papers about variational approximations to a large class of graphical models. Now that has become a little bit harder to write, but people still do it. So let's just start with basic ideas. So we could have some observations, exercise, and we could just do density estimation. And why not? I mean, after all, we find some parameters, theta, and then once we have that parameter, we draw everything. So if we truly believe that our data is normally distributed, well, we pick our Gaussian, we pick the mean and the variance, and everything's okay. Now, if the basic model doesn't actually fit the data, that's a really horrible thing to do. So, is there a way of taking our very simple devices, which are, for instance, Gaussians, and turning them into a more universal density approximation device? We want to get the more universal density estimator, and maybe we learn something about the density beyond just the fact that it's a bunch of Gaussians. Well, so an obvious thing to do is you could say, well, each instance gets its own personal Gaussian. You could do that. Now that's fine, but then it's very meaningless because in this case you completely overfit. But you could at least say, well, maybe there's a bunch of Gaussians, maybe k of them, and each of those data points first gets to choose, well, I would like to have Gaussian number 42, and then you draw from Gaussian number 42 with given mean and variance, and you get something. And this is the model that you get. Mind you, you can actually do things like that, not just over a flat structure, but you could do it over an entire tree. And so there's a very nice paper by Ryan Adams, Subin Garamani, and Mike Jordan about a hierarchical stick breaking construction for building trees. And they applied it to images. And so you get the hierarchical model of how various images depend on each other. And so they do very nice inference in that. It's a really cool paper, a really cool algorithm. And the amusing thing is that the distribution, and in particular the mean that happens on the root of the tree, out of all the images that they picked, ends up being a lawnmower. So this is the most prototypical image for all the images. A lawnmower, like to cut grass. You would think this is some, something special, like some godlike image, but no, it's the lawnmower. Okay. Okay, so we're not going to go into that much detail. There will be a class of its own in Bayesian nonparametrics, and we'll touch upon that a little bit, maybe next week, and definitely after I come back from . All we're going to do for the moment is we just assume we know the number of clusters, and we're going to draw from them. So here's what we get. So we have those xi's, and we first, decide a cluster label, and then we draw from them. So this is actually the full model, because we actually have to draw our means and covariances from some prior as well. And we draw our mixture distribution over, which variables, over the classes from some prior over distribution. So this is going to be conjugate to that. So for a Gaussian, we will have a Gauss-Wishart here. And for the multinomial, we'll have a Dirichlet here. So here we have a Dirichlet multinomial. There we have a Gauss-Wishart or a Gaussian. It's called Gauss-Wishart because basically the conjugate for the mean will actually be a Gaussian, and for the variance will be a Wishart distribution. And writing this out, basically get hold of Fukunaga's book, and he's done it at some point, and it's one very wide screen full of algebra. So here's what we get. So P of x and y, so let's pretend that we actually knew those cluster identities. It's going to be P of xi given yi, and the means and variances. And then here, of course, P of yi given zeta. So if I were to observe both the data and the cluster IDs, the inference problem here would be really easy, right? All we do is we just take the log of this, we get the sum over here, if I know it's cluster number 10, this is, what the data needs to look like, so it's just estimating a mean and variance. Here it's just estimating, cluster distribution, so everything's good. Unfortunately, we don't really know those y's, and this is what's going to mess up all of our life. I'm going to show you one algorithm, how to fix it, and then a little bit another algorithm that you can use for sampling, which turns out very counterintuitively is actually very well suited to very large problems. So, what could you cluster? Well, actually a lot of things. And basically, whenever you have a problem where you might want to hire some editors or mechanical Turkers to, take your objects and categorize or group them, you should absolutely certainly look into this first and check whether this isn't actually a good solution to your problem. Because this costs you essentially nothing, but maybe the CPU time, which is maybe a few $100, whereas a few $100 will not get you very far with mechanical Turkers, and even worse, if your distribution changes, you pretty much need to pay them again. So this is like, doing it yourself versus paying protection money to the mechanical Turkers who will hold you at ransom whenever you want to move to a different language, whenever you get distribution changes. And on top of that, they might not be very good because it's a very different demographic. So for instance, at Yahoo, the demographic of editors was more or less women between 20 and let's say 35 who, for better or worse, volunteered for the job of editors and labeling data. Now, they may be very good at their job. That said, they don't necessarily know the average demographic. So I don't know how good their labelings were on our sports page, for whatever reason. So, in other words, if you can actually use your data, if you can use your users, you're better off doing that as opposed to paying editors. So, mixture of Gaussians. It's very simple. You draw the cluster label y from some discrete distribution, and then you draw x from the Gaussian. Then we have a Dirichlet for the discrete and a Gauss-Wishart for Gaussian. And trouble starts from the fact that we don't know the y's. Now, if we knew those y's, it'd be really easy, right? Then we can just do some likelihood estimation. Furthermore, if we knew the parameters, getting the y's would also be easy, right? We could draw from them, we could maximize, you could do something. So there's a very, very old algorithm called k-means, which is not really a probabilistic model, but it's one of those workhorses where in some conferences, if you talk about clustering, they immediately think k-means and don't even realize that there's other stuff, unless you explicitly say so. And that's because it's actually a fairly robust algorithm, and a lot of good properties have been proven upon. So let's make a couple of very unrealistic assumptions. We assume that all the Gaussians have, unit variance. Uniform. I also assume that there's a uniform distribution over all the clusters. I mean, these are two things that are horribly wrong, right? And I'm going to initialize, my centers of the Gaussians by just, random subset of points. Now, the next step is I'm going to find the most likely cluster Y for any given X. Now, that actually turns out to be a very simple thing, because if I have unit variance, I just need to find the closest point. So if I have a point cloud, and I have some cluster centers. So I have 3 of them here, 1 there, 1 there. Then it's very easy for me to find out which points go where. Why? Because anything on that to the left or the right of the plane will either go here or there, right? I can draw the same thing here. I can draw the same thing here. This gives me a tessellation of the space, sometimes called a Voronoi tessellation, which tells me which points are in which region. Then anything that falls into one of those regions goes into this cluster. Then I can say, well, yeah, okay, that was quite nice. Maybe let me update my cluster center such that it actually fits those data points best. So I do that, get new centers, and then I rerun it with slightly different cluster centers, and I can keep on going on and on and on about that. So this algorithm is guaranteed to converge to a local optimum, and it's an idiot-proof simple algorithm. You can implement it in MapReduce fairly trivially, at least for a reasonable number of clusters. The updates are very, very simple, because for each cluster center now I only really need to know which points ended up there, not the ones that almost ended up there, but yeah. The problem is you don't really have a good probabilistic interpretation. You can get stuck easily in local minima. Now, people solve that usually by, you run it for a while, you take out the weakest points, randomly initialize them, and rerun it. Or you just rerun the algorithm several times with several initializations, or do anything else clever. So, entire 10-year cases, I think, have been made based on that algorithm. So, here's what you get. You initialize somehow, partition, you keep on updating, and you keep on doing that. Okay. That's the quick and dirty solution, and I think we can do better. So, that's what we're going to do now, variational inference. So we're going to learn about the EM algorithm. And, well, here's an important thing. The EM algorithm is a very specific algorithm for a reasonably specific problem. And it is a special case of a class of methods called variational methods in graphical models. So, occasionally, I get people who tell me, yes, we use EM to model this problem. And what they mean by that is, by the way, and yes, we use clustering, and we cluster the data, and the algorithm that we run in the end is EM. Okay. But that's like saying, well, I use, gasoline for driving to San Francisco. Well, gasoline goes into the car that I use to drive to San Francisco. So, the big difference between the optimization or inference procedure and the statistical model. So, try not to confuse those two pieces. It's quite often explained together, clustering and EM, just because for clustering this is, first of all, a fairly effective algorithm. Secondly, it's one of the simplest cases where you can explain EM. But there are much more general cases. And we, for instance, might actually look into, the Chinese restaurant process, basically topic models from a variational point of view and from a sampling point of view later on. And I hope that this will, settle a few issues about, the difference between method and model. Okay, so probably this beast here is thoroughly non-convex after I've done all the integration. I mean, the good thing is I can actually sum over all those yi's explicitly, so that's already easy. But I have a non-convex problem then. So, how do we solve non-convex problems? We already saw the concave-convex procedure, and that one's coming back now. So this is our objective that we want to solve. And what I'm going to do is I'm going to, decompose it into a convex and a concave part. And at each step, I'm going to upper bound the concave part by, a tangent. And I'm going to keep the convex part exact. And I'm going to minimize the sum of the exact convex part and the upper bound on the concave part. I get a new point. At this new point, I iterate again, and I keep on doing that until we've solved the problem. So, for instance, I might end up here. Mind you, there's no guarantee I end up in the global minimum. The only guarantee that I have is that things get better. There's no guarantee that I actually find the best solution. And this is something where people sometimes, use all sorts of tricks to avoid getting stuck in local minima with EMs. Sometimes, for instance, you can use stochastic EMs. Sometimes, again, you restart, and there are all sorts of clever initialization techniques to avoid this. Okay. So this is probably the scariest math you're going to see today, and it's not very scary. Who has seen the Kullback-Leibler divergence before? Good. So, Kullback-Leibler divergence is a way of, for instance, you could view it as such that it's a way of measuring how many extra bits I would need to encode data drawn from one distribution if I use the optimal code with respect to another distribution. Or actually how many nats rather than bits, but basically, how much waste there is if I use the wrong code. That's one way of viewing the KL divergence. In our case, well, we're just going to treat it as, some quantity that happens to be convex in one end. And I always forget which way around it goes, so I'm looking it up each time. So, in any case, the good thing is this quantity here is non-negative. So therefore, if I want to, maximize the log likelihood, if I get the lower bound of that, and I can maximize it at every step, then, if I know that the lower bound at the point where I start my maximization and for the next iteration is tight, I know that each step that things are going to get better. That's basically what's happening here. So I can write the log of p of x given by theta that's greater equal than the log of p of x parameters by theta minus the KL divergence between any arbitrary distribution q of y and p of y given x and theta. Well, I can always do that. And the other thing, of course, you can immediately see is that this is tight for q of y equals p of y given x. Right? Because then, on the left and right, I have the same quantity, and in that case, the KL divergence vanishes. Okay? So, this equation, the first line here should be completely straightforward. Okay. Now, to get to the next line, well, let's just write out the KL divergence. It's an integral dq of y. Now, since it's a probability distribution, I can just pull that back in since it doesn't depend on y, nothing untoward happens to it. That'll still be log p of x after I've taken its expectation. And here there are just those two terms that come directly from the KL divergence. So it's just log of p of y given x and theta minus log of q of y. So this is really just plugging in the definition. Now, the next step is also really just plugging definitions. Because p of y given x times p of x is just p of x and y. And since I have the log, the sum of the two logs, I can just pull that in and have the log of p of x and y. And the last thing that I do is I just, chunk off that last q-dependent term. So now what happens is that I have two terms. I have one where I basically have the expected log likelihood with regard to my unknown parameters. So now all of a sudden I have data. Even though it may be fake data, I have data, right? And at that point, I can pretend that I had all the data and I can get my parameters later. That's good. And here is this additional entropy term that doesn't really depend on the parameters that I want to estimate. And that only really ensures that picking p equals q, q of y given x equals q of y, is going to be the maximizer. So that's really all that there is to variational methods. So, remember the derivation. You might get the signs wrong otherwise, but you can always just redo the derivation. This is all that variational methods really are about. There are lots of ramifications, applications, techniques, tricks, and so on, but this is really the bare guts of it. And this is about the shortest derivation that I know of. I've seen page-long derivations of the same inequality. So don't be intimidated if you see a page-long derivation, just ignore it. Yep?
Sorry, I didn't get the last part.
Okay. So going from here to there?
I get up until the last equation there, but
Okay, so oh, this line?
yeah.
Well, that follows directly from here. Because the KL divergence vanishes whenever q of y equals p of y given x. So from here to there it's an equality, from here to here it's an equality. Right? Now, if this is 0, then I have an equality here as well, so everything's tight. That's all I need to start this recording. Right? So, does it make sense now? By the way, thanks for asking. I'm really glad you did. Any other questions? Because this is really important equations. Yeah.
Can you explain again what y is?
Okay, y just so happens to be some other variable. In our case, for instance, these are the cluster IDs, which would make it so much easier to deal with, the joint likelihood in, let's say, the observed and the unobserved terms. So basically think of the y's as being, the latent variables in your graphical model, which, if you knew them, you could, do the standard thing that you do if you have, let's say a directed graphical model where you observe everything, and then, inference is very easy. And so what you're really trying to do is come up with a computationally efficient device for fantasizing those y's in a meaningful way. That's really all that's happening. Yep.
So basically, that the log px theta is the thing we want to maximize.
Yeah, that's what I want to maximize.
And
I want
lower
to,
bound, and we want to prove that's convex. Or?
so the thing is that, okay, so this is actually concave in general. And I want to maximize it. So actually what will happen in general, I will also have some, log p of theta somewhere. So that will be what comes from my prime. But I just don't want to mess up, this simple three-liner with additional priors and stuff, because this is really the bare bones version of the variational inequality that you need. So I just removed everything that doesn't do anything to the inequality. And I've seen much longer derivations by very good people. And they are intimidating me. So just remember this, whenever somebody says variational, ignore whatever follows on the next half of the page and just recall that equation. It'll make your life much nicer. So here's what we can do. See, this is a lower bound. So for any given set of thetas, I can just go and pick q of y equals p of y given x and theta. In that case, at that point, this is an equality. Now if I go and maximize it with respect to theta, I know I'm also going to push the left-hand side term up because this is still a lower bound. As soon as I start, maximizing with respect to theta, this will stop being an equality, but it basically means as I push my lower bound up, the true function value can only go up even more. So reality is always going to be even better than my lower bound. And once I've solved that problem, so I get the new value of theta, I go and check again what, how I should, pick a new q. For this new q, I then again maximize, and I keep on doing that until I'm converged. So the first paper that did this was the Dempster and Rubin paper. This is probably one of the most cited papers in statistics. And they actually prove a couple of other nice things about it, and usually people ignore it and they just cite Dempster and Rubin for a yen. But they actually prove some convergence properties of the algorithm as well. So, strategy is really, you go and find that bound, and then you maximize it. It's like the ratchet. You tighten the ratchet, you maximize. Tighten the ratchet, you maximize. That's a trick. This is the entire algorithm. You apply the strategy to any graphical modeling you do. Let's look at something very simple. Let's take this as our factorizing distribution. So Q of y is just the product of Qi of y. Well, in this case, well, we can immediately work out for our clustering what Qi of y should be. So we have the likelihood of xi given yi, mu, and sigma times p of yi given theta. And I just need to normalize it, because this probability doesn't necessarily sum up to 1. So I just renormalize it and I'm done. So that gives me, given my current set of parameters, mean, variance, and overall cluster distribution, what my cluster label would be for that particular instance. That gives me a distribution. So if I have 100 clusters, that gives me a distribution over 100 different outcomes. Good. Question. If I have 10,000 clusters, is that still a good idea? No, because then I need to store about 40 kilobytes to even just store those queues. So if we have documents of maybe 100 words long and I have 10,000 clusters, well, okay, that may not be the right model anyway, but then you're basically using about maybe 400 bytes to store the document and 40 kilobytes to store this message, which means the algorithm is going to be super inefficient. It's going to be super inefficient for other things downstream as well. This is exactly why you will want to do cluster to use sampling in these situations. Okay, so let's just pretend we have a reasonably smallish problem. We know maybe a couple of 100 cluster IDs, so we get this. And now we need to actually work out the means and variances. So these are distributions. So here's what we get. So the first thing is, this is what, let's just actually work it out in detail. So, by the way, who's seen this before? Okay, about half the audience. Remember, we have E of yi times, well, parameterized by some parameter theta times E of, xi given theta given sigma. And then, yeah, let's just ignore the priors. And so we have the log of this plus the log of this. And we take the expectation with respect to Q. Now the good thing is that, and we have, of course, the sum over all the i's. The good thing is that our Q distribution factorizes. So it factorizes into individual QIs. So I can actually swap the expectation and the sum, which usually you couldn't do otherwise. So I get the sum over all the i's, expectation over q of yi of this expression. Right. Now something else that's really nice happens. Namely, well, these terms break up as well. So I get this plus the sum over the expectations of this term here. So let's attack the first term first. So this is basically just going to be, you know, sum over, you know, theta y times, in this case, you know, let's just call it qi, qi of y. And here we have the sum over all the y's. So here we have a little more theta y. And here we have the sum over all the i's. Now, that just so happens, well, to be maximized, if I pick each of those theta y's to match exactly the proportion of the, you know, labels that were assigned to that particular class. Remember when we did maximum likelihood estimation for multinomials, we counted basically how many times a particular instance falls into a particular bin, and that's what we're using here too. Except that now instances, you know, fragmented, you know, one portion falls into one bin, the other one falls into the other one. You can immediately work it out. So what we get is, you know, sum over all the y's log theta y times sum over all the i's qi of y. I'm just going to call these terms here in y. And these are the ones that I'm going to use as fractions to estimate theta y. Now, if I wanted to do a Dirichlet smoother, I would use, in the end, n tilde y plus some coefficient alpha divided by n, which is the total number of observations, plus k times alpha. And this would be then the estimate of p of y. That's what we get here. Now, let's have fun with this term here. Well, this is a Gaussian with, you know, given mean and variance. And you guys still remember how we computed the smoothed estimates for the Gaussians. And the good thing is that this decomposes into the different, well, here we have y, right? This decomposes into, you know, basically one Gaussian for each cluster ID. So I can just, you know, solve for each cluster ID separately. And so what I get is that for the mean, I just have the sum over qi of y times xi. And I might actually go and smooth this, right? So I might smooth this plus, you know, m0 times 0 as, you know, my mu hat. And then I might go and use the sum over I, q of I of y, and of course I need to normalize here y, sum over I, q of y plus m0, this expression here. I get the same thing there, sum over I, q of y plus m0, q of y times xi transposed, and then I get my smoother, so I get m0 times maybe the unit matrix, this here minus mu hat transposed, and this is my estimate for sigma. So that ensures that, you know, I don't get, you know, zero variance. So even if some cluster happens to be super unlucky and not really get any points at all, my variance isn't going to go to something insanely stupid, because basically then this term really has no effect, and it's just going to be unit variance. And once I have these guys, I can recompute the new set of Q's and iterate. Quite often you would see that type of algorithm without the smoothers, but it's just so much more stable and robust if you smooth. So don't implement it without the smoother. So here's what happens if you actually run it. And yeah, I think it was a plot from R. We've dealt with this part. The estimates will actually diverge and all that. And I think now is actually a good time to stop, because the hidden Markov models will keep us fairly busy next week. So this week we've gone through things a little bit more slowly than before. Before I finish, I'd like to have a brief vote from you guys. How's the speed? Is it better this way, or is it worse this way? So who votes that it's better? Okay. 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 Who would like me to do things faster? Okay. Who would like me to go through things even more slowly?
Depends on topic.
Okay. Good. Okay, so I just hope I didn't bore you too much by going through it a little bit more slowly, because I figured, yeah, otherwise it's probably a bit hard to follow. Okay.